this activity, we're going to look at the same open loop transfer function for our system, this motor position control system, and we're going to try to achieve the two time domain specifications that we were not able to achieve with proportional control, now using a PD controller. And so now we have a zero location and a gain for the root locus to integrate and essentially pick those locations and those values in order to achieve these time domain specifications. So give this a shot using the RL tool. You can either enter in this transfer function for the plant and this transfer function for the controller in RL tool, or you can start where you left off in the proportional case and select that edit compensator option. If you do run it from the MATLAB window, you'd call RL tool, and then you'd write in your 1 divided by s divided by s plus 1 as your plant, comma, and then what you do is you would give it a transfer function, and you need to give it an initial guess of this this zero location. So in this case, you don't want to put it, say, at the same spot as this pole, so maybe I'd go ahead and place it at 2. And I would run with this. The fundamental difference between putting in terms in this first term and this second term is that items in this second term are adjustable and movable within the RL tool. So this 0 will show up red and will allow you to move it around, whereas these poles will show up blue and you won't be able to move those around. So go ahead and give this a shot, see what kind of options you can come up with, and I can show you the different solutions that I see. Okay, so our design specifications have not changed. We have the same system, we have the same criteria here for our time domain specifications, and the only thing that's changed really is the fact that we have this extra 0 to play with. And these 2 degrees of freedom end up showing us that we do have access to portions of the complex plane to put our closed loop poles so that they achieve these time domain specifications. So typically that means that there are many solutions, and there's still a trade-off. Achieving overshoot and achieving rise time are competing goals, and so there's still going to be this trade-off that we saw in proportional control, but there are going to be solutions that do exist. And so kind of what we're going to see in the RL tool is that the influence of moving the pole location to the left leads to something that creates more overshoot, but is better for the response, the rise time, and moving the 0 location to the right leads to a slower response, but a better overshoot. And so let's go ahead and jump into the RL tool and take a look at this example. All right, jumping into the RL tool, we can either call it directly from the command window, and here again we'd put in a value for that 0 location for our PD controller and hit enter. What I'm going to do is I'm going to start where we left off on the proportional controller, so that way I don't have to change any of my my time domain specifications that I've already pulled up here. So what I'm going to do is I'm going to go into the compensator window, and I'll select right click here and click add pole or 0. And it's going to be a real 0 because that's going to be a single 0 that's on the real axis. And so by default it puts it at -1, but I know I have a system pole that's already in that location, so I'm going to go ahead and move it over to 2. And so that now creates a new, different looking root locus that now we can try to shift around in order to achieve our time domain specifications that we want. So now there's going to be many, and so the idea is to simultaneously move the K value. So you can imagine that moving that K gain, that single K gain that we have access to, moves us along the root locus. But as you can see right now, we're not seeing there to be good options, because if I were to move these poles further, I get to the point where now one pole, closed loop pole, is satisfying my behavior and one is not. And so it's possible that this configuration, so what we see here is that this actually does end up satisfying our two design criteria, but it's a little bit more uncertain as to whether that's going to be the case or not. So again, these do look like reasonable values. One reason why we might not choose these, though, is that because it requires a very large gain. And so that gain, again, the best intuitive explanation is large gain is like someone that's driving a car with a lead foot. And so it leads to a very stiff system. You can imagine that's similar to spring constants that are extremely stiff. And so those end up with very harsh control laws. So in general, we try to steer towards controllers that that lead to smaller inputs, and a small gain is a good way to ensure that. So there are ways to achieve this, but we are using a relatively large gain. In this case, it's about 12. So what another option is that we can move this 0 around and shift the location of the values and the values of the closed loop poles that we're able to achieve. So what you'll notice is as you're moving this, the root locus gets a little bit choppy, but once you release it, refines it a little bit better. One of the things that you should be using while you move in this case, the 0 around, should be your intuition about how the root locus is sketched. For example, you'll notice that as we change the 0 location over here, we're really just kind of increasing the size of that circle. But we know that if we were to move this 0 location to in between the two original open loop poles, that would substantially change what the root locus now looks like. So now what we get, now it's a little hard to see because I've got this pole all the way out here. If I were to bring it back, now what you can see is you've got the root locus on the real axis in this small region here, and then on this section. And that really is due to that rule that says that it's on the real axis to the left of an odd number of poles and zeros. And so this kind of shows that it's probably a bad idea in order to place our poles like this. We do see that we get some interesting behavior here. Here we're getting an overshoot that is very small, and that your rise time is actually rather short, still outside of our time domain specification that we want. But it also has this kind of long-term, it takes a full 5 seconds for it to get, maybe 6 seconds for it to actually get there. So we'd like something to happen faster. And so one of the ways of doing that is to pull our closed loop poles a little further away from the origin. So now that we have this, we could move our 0 around until we find a good spot. So now we can see that there's lots of different solutions. So one could be somewhere around here. We'd expect maybe it could even be a little bit more aggressive. So we're looking at the overshoot. It's at 8. I can try to increase that a little bit more. So right about, let's see, right about there. That allows me to get pretty close to both of my time domain specifications. I'm at 9% overshoot. This leads me to believe that maybe I could move this 0 around a little bit more if I wanted to try and push this to exactly 10%. And again, the only reason why you'd like to do that is that might allow you to reduce the gains that you're using to achieve these two time domain specifications. So in this case, this corresponds to a pole location of about minus 2.2. And the MATLAB gain that we use in that case is this 5.9. I'm going to show you when we go back into PowerPoint, I'm going to describe a little bit better about how this gain relates to the gain that we actually design. You'll notice that this is in a slightly different format. It's 1 plus 0 plus 0.45s. So usually we write it S plus Z. They've divided by a quantity, and the reason why they do that is they like to provide what's called the DC gain of the overall loop transfer function, and that is the DC gain is when the frequency is 0. And so if we were to plug in 0 here, the controller in this case would have a gain of just 1 times this gain. And so writing all of the terms like this allows you just to read this off as the actual DC gain itself. And so that's why MATLAB chooses to present it that way. So I'll show you how to compute the way that we usually write it is really just dividing by this 0.45 in order to figure out what the actual gain is. So this is a solution. This would be a fine solution to give. Again, if you were to work in practice, you might fiddle with this a little bit more in order to get a little closer to your 10% overshoot. That way we could adjust this DC gain to be a little less than what it is right now. We saw in the RL tool a couple of different ways in which we can identify solutions that meet our time domain specifications. There are a lot of solutions in this case. The one that I'm depicting here has a 0 value right here, and the corresponding gain that I selected is this. And so keep in mind that these are values that come out of MATLAB, and so it's really defining the controller like this. And remember that we said that K is essentially what we called our KD, and K times Z is what we called our proportional gain. And the reason why these are the important values is because our control law U, what our feedback control law U is it's going to be KP times the error, the tracking error, where that is R minus Y, and that's going to be added to KD times the derivative of the error, and that is the derivative of R minus the derivative of Y. So we're literally plugging in these values and multiplying it by these two gains in order to get our input U. And so this could be, for example, the amount of voltage that we would add, or this would be the amount of torque that we would be adding, something like that. And so you can imagine that if we're dealing with a mechanical system, and that U represents a force or a torque, it makes sense to make those as small as possible. And so that's the reason why we often look for gain values that are small. And so to make sure that we can get all the way back to these values, it's useful to think about when we have our items that come out of our design criteria that come out of MATLAB, it comes in this form. And it's useful just to be able to feel comfortable rearranging this into this format, which tells us the actual gain that we called K, and this is the 0 value Z. And so really the 0 value is not changing because that's what we already picked out right here, but the gain here is a little bit different. So that's 5.8, and the actual gain that defines the derivative gain is 2.5. And so it's useful just to understand how to get from here, and really you can think about it a couple of different ways, but effectively you're taking this value and pulling it out, and so that's why this 5.8 gets multiplied by this to get this overall final gain value, and then dividing or pulling this out creates the 0 value here. Notice that again we talked about this as being the DC gain, and that's when S is equal to 0. Notice that the DC gain, when this S is equal to 0, the DC gain is 2.5 multiplied by 2.3, and that's what's going to give you this 5.8 back again. So that 5.8 represents that DC gain, and that also does represent, in this case, our proportional controller gain value. So that's also a useful number to understand. So we saw how the proportional control was able to achieve our objectives, and now we're going to introduce a couple more sophisticated controllers that give us extra degrees of freedom for our controller designs.